For over a century, the electrical grid relied on the physical momentum of massive spinning turbines in fossil fuel power plants to maintain stability. Today, as renewable generation replaces those traditional plants, that heavy physical machinery is disappearing. Without massive steel turbines spinning in sync, the grid loses its physical inertia. This makes the overall system frequency highly volatile. A sudden drop in power generation can cause the frequency to drop in milliseconds. To replace that lost physical momentum, grid operators rely on battery energy storage systems, or BESS. These massive lithium-ion installations act as a high-speed digital substitute for physical inertia. The primary service these battery systems provide to transmission system operators is called fast frequency response. They constantly monitor the grid and inject or absorb power to keep the frequency locked strictly to the required standard. The most aggressive form of this service is known in the UK as dynamic containment. If a major fault occurs, like a power plant tripping offline, the battery system must react and deliver its target power in under 1 second. Consider a typical 50-megawatt BESS unit. In response to a frequency trigger, its inverters can flip from full active power import to full export in less than 1 second. This sub-second response time is necessary to arrest frequency deviations before they breach statutory limits. But by moving power this quickly, the battery introduces a new mechanical stress to the local distribution network. While the national transmission system operator is focused on stabilizing the macro-level frequency, the physical impact of that rapid power swing hits the local distribution network operator. This animation illustrates the relationship. The bar chart on the left represents the active power output of a battery system shooting from deep negative to high positive. As that power rushes into the local network, the steady sine wave on the right reacts by warping and compressing. The battery is successfully correcting the national frequency, but the sheer force of that localized power injection causes a severe transient wobble in the adjacent voltage waveform. Engineers define this localized wobble as a rapid voltage change. This creates a direct conflict in operational goals. The transmission operator demands instantaneous power swings to keep frequency stable. The local distribution network requires smooth, steady output to keep voltage stable. If these rapid voltage changes go unchecked, the localized dips and swells can trigger protection relays or cause nuisance tripping for connected industrial facilities and residential neighborhoods. Stabilizing the national frequency creates a persistent voltage regulation problem for the local substation. To understand why reversing direction causes these rapid voltage changes, we must look at the physical behavior of a single battery inverter during a frequency event. This graph plots active and reactive power. Battery inverters have 4-quadrant capability, operating anywhere across these sections. During a fault, a battery in the bottom left charging quadrant shoots to the top right discharging quadrant. Notice as it crosses the zero power center. At that exact millisecond of zero power flow, the battery is in a no-load condition. In that window, the local grid voltage is dictated purely by the background system voltage. If the surrounding distribution network has a weak short circuit level, this rapid unloading to zero, followed instantly by a massive reloading, creates a transient voltage swell. Reversing power flow through zero is what actually stresses the local network, independent of the total megawatt volume. Because extreme power swings are a designated feature of normal battery operation, grid operators require a strict rulebook to measure and limit the resulting voltage disturbances. In the UK, this is governed by an engineering standard known as EREC P28 Issue 2. This table categorizes rapid voltage changes based on expected frequency: frequent, infrequent, or very infrequent. Category 2 infrequent events allow maximum 4 events per month. For battery balancing the grid minute by minute, this limit is easily breached. This square wave diagram defines thresholds for frequently operating equipment. The sudden voltage change is boxed within +6 to -6% boundaries. Within 100 milliseconds, it must recover and settle strictly within a 3% steady-state limit. Beyond sudden individual drops, the continuous ramping required by dynamic services causes ongoing repetitive voltage disturbances. The standard measures and restricts these as short-term and long-term flicker. Currently, network operators refuse to exempt battery systems from compliance with these limits, even when the battery is responding to an extreme abnormal frequency fault on the wider grid. To secure a connection agreement, a developer must mathematically prove their highly active battery system will stay entirely within these rigid static envelopes. Proving compliance for a single battery unit is straightforward. The real issue scales up when we look at the regional level, specifically around a major grid supply point. Here, distribution networks face their primary nightmare scenario, the coincident power swing. Developers often cluster multiple independent battery projects around any substation with available capacity. Imagine 3 distinct facilities tied to the same local grid. When a system-wide frequency drop signal arrives, all 3 trigger at the exact same millisecond to respond. These dynamic simulation graphs prove how synchronized reactions compound local disturbances. The top graph tracks the frequency dropping below the threshold. In the second graph, separate battery outputs perfectly overlap, causing the severe cumulative voltage drop seen on the bottom busbar graphs. This creates a dangerous cross-voltage interaction. A voltage drop on the high-voltage transmission interface propagates directly downward, exhausting the voltage headroom for medium and low-voltage networks. The result is a localized voltage collapse that exceeds the standard limits and threatens the stability of all nearby interconnected substations. A single 50-megawatt plant might pass compliance in isolation, but the synchronized reaction of multiple units creates a cumulative voltage drop exceeding safe operating limits. To prevent this, developers mathematically prove network stability long before any concrete is poured on site. Engineers rely on dynamic RMS simulation software, like Digxelant Power Factory, to map these complex network interactions. The core requirement of these connection studies is that all simulations must be tested against the local grid's minimum fault level. The minimum fault level represents the grid in its weakest possible state. When fault levels are low, the network exhibits the highest possible sensitivity to rapid voltage changes. Developers input strict parameters, forcing the model to run transitions from full import to full export over a mandated 1-second ramp period. Running these aggressive, worst-case simulations is the only reliable method to expose hidden voltage violations and prevent real-world grid instability before a battery system is ever connected. If a proposed battery site fails the simulation, engineers cannot change the physical grid infrastructure. Instead, they must constrain the battery's control logic. One common mitigation policy forces the battery to operate at a strict unity power factor during dynamic services. This effectively eliminates reactive power swings, preserving local voltage headroom. A secondary mitigation involves configuring the battery to carefully time its active power swings, ensuring they do not conflict with the observation windows of the local transformer's on-load tap changer. With these mitigations applied, the active power swings rapidly to save the national frequency, but the local voltage waveform remains steady, locked safely within regulatory limits. The transition to a zero-carbon grid demands energy assets that can react in milliseconds. However, that sheer physical speed is destabilizing to local infrastructure if left unmanaged. By rigorously applying engineering standards, simulating coincident swings, and testing at minimum fault levels, engineers are mastering the physics required to safely power the renewable grid of the future.